всем привет. Спасибо, что пришли. Сегодня я хотел бы вам
Thanks very much for joining me here. I'll talk about reversing operating systems safely. Do this reverse engineering. With this particular example, I may be referring to this one particular operating system. I'm Bulat Zagardinov. I'm in for research of these prospects of red teams and tackle the safety of industrial solutions, industrial devices. I start with this global platform specification, which allows to understand the intention of the safe operating systems. It's trusted execution environment where we launch trusted code. One of the specifications of a global platform, that is system architecture, stipulates an interaction of rich in execution environment and safe execution environment. It's one of the specifications that describes the interaction between different components. That is, sending commands, how exactly these commands are sent, how we send blobs, etc. This is approximately what this specification looks like with the main functionality of a safe operating system. And the safe operating system, just like in the normal world, its own kernel runs with its own applications running on this kernel. For example, in the rich execution environment, we may have Linux running with some applications running on it. In a safe application system, we have trustlets. Trustlets also have APIs used to complete and realize their functionality. API is described by global platform specification. It's recommended to use in reverse engineering because this is the standard they stick to, so it would be very convenient to move these trustlets there. Core API looks like this, like you can see right now. It's used together with trustlets, and you can read in the description what the arguments there are, what's pros, what's the cons, etc. There are a few standards like that, so they describe the customer side, the client side on the rich execution environment and the interface of the safe operating system. It's very recommended to use in the reverse engineering and restoring the logic of everything. In order not to start reversing some proprietary solutions, in order just to understand how it works, we may want just to check out this good open source examples. OPTE, it has its source code, some proprietary resolutions and trusted environment for Android devices. They very often take OPTE, they modify it a little bit and sell it. It's not quite legal, but that's what it works. If you're already familiar with this particular realization, some of the TE realizations can be reversed in a much easier fashion, in a much simpler way. TE is used here in the devices based upon Android, in the Internet of Things, where trusted computing is required. It's also used for TPM implementation. According to TPM implementation, the trusted component should be implemented for PC devices, but trusted technology, which develops the TPM standard, agreed with global platform to make sure that they facilitate the development of such versions in TEE, and AMD and Intel realize FTPM. these days, if I'm not mistaken. Speaking in terms of AMD, I know how they do it, and I'm going to tell you this story. In 2015, AMD introduced platform security processor, which is standalone core running on the main CPU chip, from which all the upload starts. Before this code starts in n86 kernels, ARM kernel starts, which verifies secure input for the main system and also enables some additional mechanisms, including FTPM. In PSP, at the initial phase, PSP OS initiates. This operating system has been studied properly by the colleagues of mine in the British University. They developed an open source tool, a PSP tool, which parses the file system for that particular operating system. In an initial stage, on an allocated core, this proprietary operating system starts, initialization occurs, and they created and they considered all of the architecture for server processors, but they left the part with the Ryzen CPUs unexplored. I mean, how the safe operating system works, how this firmware TPM is realized. This is an integral part of the contemporary operating system Windows. Starting from Windows 10, the use of TPM is very relevant. They also made a little bit of a mistake, saying that the operating system running in PSP is AMD TEE. It's not true. AMD realized their own solution, their own version of a safe operating system, because one of the drivers which is responsible for PSP interaction with Ryzen CPUs has trustlets for KNB. It's a trick from AMD, maybe, or maybe they wanted to make it compatible with KNB, I'm sorry, but I don't know, but that's what it is. In order to start this analysis, first of all, we just need to get the firmware, get the code which runs in PSP, which is a part of UEFI image, and we can get this operating system from there. We can extract it from there, like we can see it on the other slide. They developed the PSP tool, which parses UEFI image and extracts the file system, PSP file system. It's just one of the blobs that needs to be parsed. And they developed a utility which parses it, pulls out all the contents, which you can study later on. And also it has an image of a safe operating system in there. It's entitled AMD TEE. That's the name of the operating system. There'll be nothing but strings, like it always happens for proprietary operating system. It has minimal functionality, no debugging is required there, no information is contained in the strings. We just need to analyze the naked binary, so to speak. We know that it starts with the header, PSP file system header, and the next part, well, you can give it a guess here, who's already been studying binaries. It's the ARM code. You can tell it by these symbols, little ID, etc. just by looking at this code. Before analyzing this code, you just need to take a look how previous stages work. PSPOS runs at the previous phase. From this study, we understand that TEE overrides PSPOS. It sets it to 0. How does this happen? If we open the TEE loader in PSPOS, we will see that here in the destination address we have a symbol which is defined here. It's a place in memory where this TEE image is written. 28 entry type is a driver which maintains compatibility with platform API. It writes to address, and the code starts executing not from the horizontal offset. You can see the first argument 0. Operating system has not been initialized yet, but it's trusted to start and run the trustlets. While disassembling the beginning of the code, the start of the code, and comparing it with the information from previous studies, we can see this exception chart. Exception offset can be addressed here, and system calls. And we can also see, after it's been passed to TEE, execution flow deploys, which registers are initiated, etc. Before AMD TEE starts its main logic that I'm showing here at this particular slide, it checks and verifies whether MMU is a functional memory managed unit, whether it is functional. It shuts it down, copies it to the 0 address, it copies PSP OS, and TE seems like it's the only thing running on that CPU. I'm talking about Ryzen CPUs. After this initialization, we can only interact with TEE, and there is nothing relevant for EPIC if we are talking about Ryzen CPU. What I'm showing here on the slide, it's colored by light green by a special plugin. I would like to thank its creator for doing so. It highlights the names of the system registries by ARM that are used for hardware setup. All these registries are set to default zeros. And here we can see the vector chart. This table contains the exception offset rules. This is in the registry bar. So the basic 0 address has been given properly. That's what we need to verify. Then MMU shuts down so that AMD TES can handle the virtualized memory. Cache is validated, and in a special register where we can see the main translation table, we see some addresses written down in the memory where we can track down the initialization of memory. The initialization of the initial memory is done by this init memory. It is done like this. Mainly, it translates whether there is physical space there, physical address space, rather. But we can also see that some parts of memory from 0x00 to 15,000 is depicted for read-write and execution. This code is contained in the AMD TEE. That's the initial process, init process. With the bootloader arguments addresses, we used to have boot ROM, and now they are rewritten by such ones for AMD TEE. Then we launched the main init process. Additional virtual memory is used, randomization is used here, and init process is added to the queue. This what it looks like approximately. What's interesting here is that the first argument is entry, the entry of our task. So the unit here is a flow in the operating system. Every task may have a few flows, and the time is distributed correspondently by flows. Why is it important to know how this function operates? Because it's used through a system call to create additional tasks. So here, special registry is set, which stipulates how this code is running. Security ID is set here, and we also set the priority of the process. We can also see the size of this structure here. After this init process is launched, it carries out stage 1, where I would like to omit the details, but we need to consider some system calls. It revokes a part of the memory, some part of RAM, 64, 63, 73 calls, 78 and 80 return this physical address when necessary for some registries. As for task management, there are some tasks for creating tasks. We can share IPC, of which I will speak a little later. The most frequent call in FTPN is F2 IPC to the driver, which realizes global platform. We can put this task on hold, and we can check out some other options which I haven't checked yet myself. Then it goes to init stage 1, where the main translates are loaded there, and external commands processor. For example, one of the interesting commands is the upload of their own translate. We'll talk about it more in detail further on. Here is the structure. That's what it's shown. Here is the signature part, which is not utilized here. And there is a version of a header. In some of the version we have an additional code which is split in 2 parts, and there is nothing else to comment on. And also this canary, which is not static. So canary is used, which randomizes at the launch of the trustlet in order to call all these functions, in order to reach the API from stage 2 init process, which realizes some of the commands. In the Windows, there is an AMD TEE library where you can pull out such functions. So each of the commands corresponds to a certain function. All of them stand for global platform, and that's what we need to know. What else can we do with it? Like I was saying, there is no verification of the signature, so you can upload your own translate and see what happens. Restore logic, develop an emulator, and to fuzz the interface to upload the trustlets. Instead of verifying the signature, they verify the props. According to their specifications, trustlets should have props, and one of these props is the application ID. I'm done. Thank you very much. Do you have questions?